we had certain topics that seemed to be kind of popular, and so this year half of my groups did something with drones. And this one has really more to do with protecting the investment that you have in your drone. We were donated a drone by a company we do some research with, Duro UAS, and they had kind of broken it and said, if you can fix it, you got it, right? And so I actually had a student fix the drone, and then she did some research with it, and then she managed to crash it. And so we're learning the hard way that these drones need some sort of help in order to protect them. So we'll let the group take it from there.
All right, well, good morning, everybody. This is another drone project. Our project name is A Safer Drone. This is our preliminary design review for our Capstone Senior Design Project for fall 2017. So I'm going to send the agenda for you guys tonight, or this morning, so that's what we're going about. So first we have our motivation, what actually inspired us to start this project, introducing ourselves as a team, going over requirements such as system requirements, engineering, electrical, and software requirements, project description, what our project actually is and what it does, system design, risk analysis, test plan, and finally our cost and schedule.
The Federal Aviation Administration registered 770,000 drones since 2015. So as the number of years increase, the number of drones and the number of crashes has also increased. Drones can crash from anything from trees, walls, airplanes, and other drones. So how can one protect their drone? There are collision avoidance products inside the modern day world right now, but they are usually expensive and have limited use. DJI, a well-known drone retailer, sells their drone for $1,500, while the guidance system ranges from around $1,000.
And so we bring to you a new solution in the Safer Drone. Safer stands for sense and avoid foreign entities real time. Our solution will be one that is affordable as well as universal to all drones in the market. This slide is black. That's fine. So we're just going to introduce you to the team behind Safer Drone. I'm Jaspreet Singh. I am the project manager and systems engineering lead.
I'm Stephen Forte. I'm the electrical and hardware engineer.
Curtis Nicholas, data analysis and software engineer.
And I'm Kristen Contreras, and I'm hardware and education and testing. So, breaking down the main requirements, our collision avoidance system must be able to detect both static and moving objects within a 5 centimeter to 350 centimeter range. And the total cost of our product must not exceed our $250 budget. So, regarding the software, our code must be interactive, and our embedded device driving system must be able to handle multiple processes at the same time. So it's also important to note that our system must utilize standards so that it is adaptable to multiple purposes. And lastly, like all drones, our system must adhere to FAA standards and regulations. So here we have our product description. Based on conducting a series of different trade studies, our collision avoidance system will be manually driven with automatic intervention. We will be using ultrasonic sensors to detect objects in the environment, and we also will be using a Raspberry Pi to process that information. So to the right of your screen, you will see our system's physical diagram. We have our user controller, our radio receiver, our Raspberry Pi, our ultrasonic sensors, our DJI flight controller, and our DJI Phantom 2 drone hardware. determines that the force of attraction towards the target plus the force of repulsion from the object detected equals the resulting force vector. And the direction of that resulting force vector is the Joule strain rate point. So here we have our safer drone operational view. As you can see here, first our user initiates flight. Once the drone is in the air, it constantly switches the environment for objects that may stand in its path. If a collision is predicted, then automatic intervention takes place in the efforts to avoid collision. And once the drone senses that it's in a safe environment and no obstacles seen in its path, then manual control is then passed back to the user. So here we have our safer drone behavioral model. As you can see here, next the user initiates flight with the remote controller, our radio receiver receives its commands and transmits that information to our Raspberry Pi. If our ultrasonic sensors detect an object in its path, then that information gets and then the Raspberry Pi then determines the threat of that situation, and automatic control or manual control is then passed to our flight controller. If the user decides to terminate flight, then our drone decides to land safely on the ground. Otherwise, commands are then routed back to our receiver, and that information is transmitted back to the Raspberry Pi, and the whole detection process restarts again.
This is the standard that we're using for our project. This is the EECE410 protocol inverted UART. The EECE410 is a high-speed serial protocol that we're using for the digital data transmission and receiving of the microcontroller inside our drone and the flight controller. We're going to be using our Raspberry Pi to interface that and interrupt the communication links between them. We have a single line support, which supports up to 16 servo motors, and it supports most flight controllers. Here we have the configuration of the EECE410 protocol. We have a 25 byte message, which one byte is separated into one start bit, two stop bits, one parity bit, and 8 data bits. We have our risk analysis. We have the sensor inaccuracy, where if we have a large margin of error, we're trying to increase that. And if our average is equal to the accurate measurement of our ultrasonic sensor, we're trying to mitigate that by using the common filter. The common filter will be able to help reduce the errors inside our ultrasonic sensor. We have the maximum drone stop distance, where more distance needed for sensor detection. We're trying to mitigate that by multiple testing and simulation to analyze the stop distance and also limit the max speed of the drone. Hardware failures, what if the Raspberry Pi dies right between drone transmission and can no longer send signals? We're trying to mitigate that technique by maintaining existing fail-safe mechanisms. As in, if the drone detects that the Raspberry Pi is no longer connected and can no longer send or receive signals, its fail-safe mechanism is to return back home. We have our ultrasonic sensor actual and measured sample data. In this graph, we have the average being consistent, while the actual individual values are very distorted and show some range. There are some false positives inside this graph that is not shown. If you would like more ultrasonic sensor test results, you can refer to our appendix. Here we have the common filter. We have 3 parts to the common filter, which is to calculate the common gain, calculate the current estimator, and the new error in the estimator. What we're trying to do first is to calculate the common gain, where we have an original error inside the estimate. We have an error inside the data, the measured data from an ultrasonic sensor. That is computed, and therefore we're giving the common gain. If the error in the estimate is low, we're going to try to put more significance on that, and vice versa. If the error in the data is low, we're trying to put more significance on that. We then move on to calculate the current estimator, which has inputs of the original estimate and the input data. This shows 2 results, which is the updated estimate and the new error inside the estimator. The common filter is used for mitigating the error inside our ultrasonic sensor, therefore giving us real overtime package?
So the experiments that we're currently working on and plan to test early next semester involves using Verilog and the DE0 Nano. So using the DE0 Nano, we will measure stop times at various speeds with gravity sensors. Basically, the motivation behind this is to measure stop times it takes for the distance for the drone to stop. So we'll use this using a clock divider. So basically, when the drone is leaning back to decelerate, the gravity sensors will activate and start to counter. And finally, when the drone is into rest state, the gravity sensors will deactivate and will stop the counter. That way we will know stop time. Now using this stop timer, using these physics equations here, we'll be able to calculate deceleration and stop distance. Now the final distance or final velocity is 0. The initial velocity, we'll be able to calculate deceleration, and then knowing all that, we will be able to calculate stop distance. So the goal of this is to create a MATLAB simulated model with the above parameters. So this is the layout of the previous slide that I just mentioned to you. So basically the drone is flying along. Finally, when the drone decelerates, it's going to tilt, which activates the gravity sensors of the DE0 Nano, which in turn starts the counter. And finally, when the drone is in its resting state, the gravity sensors deactivate and stops the counter. So here's another test that we're planning for next semester. This does not involve the vector diagrams like Kristen mentioned before. This is simply just testing the drone to see if it will stop in front of certain objects and if it's detected by the ultrasonic sensors. So as you can see from this flow diagram here, we will test the drone with flat objects, such as like a cardboard board, something very flat, something with a big cross-section area so the ultrasonic sensors can detect easily. We will test it at low speeds, and if that's successful, then we will move to high speeds with flat objects. If all that is successful, then we will move to narrow objects such as a pen, something like that will simulate a tree branch, something very thin. That has a small cross-section area that will be harder for the ultrasonic sensors to pick up. So then again, we will test that at low speed. If that's successful, we will move to a high speed. If that is all successful, we will continue making improvements to the system. If not, then we will go back and do adjustments. Here's a quick look at our bill of materials. Again, since we already have our DJI Phantom 2 supplied to us by Dr. Boron, that cost is not included, and we already have a Raspberry Pi, so that is also not included. But in terms of the items that we do need, miscellaneous includes wires and resistors to interface the Raspberry Pi with the ultrasonic sensors. That comes to about $1265. Also associated with Raspberry Pi, we have the Raspberry Pi battery, and we have the charging board, light bulbs, and micro USB port. Total that equals $18. And then finally, your ultrasonic sensors, it's $4 for the unit price. Like we said, we will be using them, so that equals $32. And then a custom PCB board, there will be 1 per unit, but we bought in bulk because it's cheaper. So total that is $46.79, with a total price of $109.44.
So as mentioned earlier, we designed a custom PCB for our project. The goal of the PCB is to facilitate mounting and wiring of the system. We want to create a solution that is easy to mount so that a user can apply this to the drone without having to drill any holes in their system. As you can see, we have cutouts for the landing gear, as well as mounting holes which align with the existing mounts for the camera. It should be noted that we can still attach a camera to the bottom of this PCB if necessary. Also, we've laid out the ultrasonic sensors evenly around the disc to provide maximum coverage and minimize blind spots. So here we have an estimated cost analysis. We've estimated prices based off of bulk for under 100 units. So theoretically, if we were to ramp that up, we could minimize cost and improve profit. The total cost to build the system is about $100. We could mark that up easily about 35% and still sell it for 15% of the cost of DJI guided system. So here's a project plan for us moving forward. We are currently pens down on our design. In the upcoming weeks, we plan on conducting some simulation, as well as begin ordering parts for our system. We hope that by the first week of February, we'll obtain all our parts so that we can begin hardware assembly in parallel with coding. Hardware assembly will then become system integration between the hardware and the software that we have developing. And we hope to give ourselves at least 1 month to test and debug our system. On the bottom, you see our progress as a whole. We're currently using an agile methodology of development for our system. As such, we've estimated about 135 points towards completion. As a result, we're at about 36% completion currently. So in summary, our first priority is to provide safety for all drones and their flyers while maintaining affordability. We want to provide a solution that is universal, not just for drones of the DJI brand. Most importantly, our biggest advantage is that we are theoretically selling a standalone system with easy install, so anyone who can plug in a wire or two should be able to install this on their drone. Thank you for your time. I'd like to open up the floor for questions. first I'd like to mention that in our initial testing, we will be stopping the drone, but moving forward, we'd like to do the object avoidance that Kristen had in discussion with this was your slide.
Right. So, like we said before about like the force fields and the obstacle knives and certain purpose and everything. So basically, if an object, so this would be the detected object, and this would be the target. So say like you want to fly the drone in a certain direction, just going towards the target. So basically, the force towards the target, that attraction force, plus the repulsion force from that detected object, reaching a wall, whatever. The resultant force of that, the summation of that is equal to the resultant force. And then once you get that resultant force, that object goes into whatever the direction of the force vector is, and it would steer in that direction. So that's the direction.
Would it take control of the drone itself and stop it? Or would the user heads up?
So we're passing all the information through the Raspberry Pi. So the Raspberry Pi is constantly seeing what values are being passed to it. So there'd be no interruption of the signal, just a seamless transition between going forward to now turning. Okay.
Thank you.
How many degrees like of view does your sensors have? Like, do you have any blind spots in your sensors?
Yeah, so I conducted a trade study on the ultrasonic sensors. I don't believe we have it listed here, the angle, but actually we do have test. Sorry, go to the test result. Yeah. So we did conduct an extensive test result. The image is a bit blurry, but we calculated for a flat object around a circle. We did up to 30 degrees either way. Objects were detected up to about 20 degrees before they could not be seen. But the actual product, the ultrasonic sensors, they're marked with about 11 to 15 degrees accuracy in either direction. So we could achieve up to about 20 degrees, but the data sheet says 11 to 15 degrees in either direction.
Do you have like sensors on the top of your drone also, or it's only like if there's an indoor? I don't know if you'd be flying indoor, but in any case, would you have sensors on top as well to avoid hitting like the ceiling?
So you're facing up?
Yeah.
We've actually not thought of that. That's a good question. That's something we could definitely consider, but the drones that we're flying are for outdoor purposes, so theoretically should not hit the sky. But of course, if we were to market this for indoor drones, we could consider that. That's a great question.
What is the total number of sensors on that machine?
There are 8.
Okay, I think we need to try to move it on to the next group. The next group